Alright guys, the video frame buffer board. Without even pulling out the schematic, I've just started. I love how Berzerk boards are laid out. It has everything sectioned off. Right here is your timing and control logic for this board. And then you have that's not labeled. Weird. Horizontal address counter. And here we have vertical address counter, these two chips. So you see everything's kind of labeled. Horizontal and vertical timing. Yeah, anyway. I just started. Let's start at the beginning. Let's look at horizontal counts. Horizontal address counter. We have clear is high all the time. Here's your clock. And inputs are probably all tied high, which I would imagine is. And this is one of the enables, which is held high, so it's always enabled. There is no load, so this just free runs. And this is the other enable, which is high. So this thing should just count from 0 to F. It should count from 0 to F and then just keep going with a terminal count or a what you call it, a carry bit. So here is the least significant bit, which is 2.5 megahertz, which is fine. The next one is 1.25 megahertz, fine. This one should be 750 or something like that. 650, 625. Okay, fine. And then this one is high all the time. This one's not doing anything. You can see that auto is not triggering, so this isn't doing anything. And there's no terminal count. And that terminal count is what will go down and enable the second one. So this second counter is not counting at all. It's not doing anything. Here's the first bit, second bit. It's just not counting. There's no horizontal count on this second guy at all. On this guy, there's no count because this one right here is no good. So that chip's definitely no good. It's a 161. You can use a 163 in there because pin 1 is tied high, so 161 or 163, and whichever you got more of. Yeah. And the vertical counts are going to count off of this second horizontal count, I would think. It's typical. Yeah, see there's no vertical count. That's vertical addressing. So horizontal and vertical addressing is non-existent on this board. So we need to fix that ASAP. So let's go ahead and replace this guy right here. Okay, one step at a time. We now have our counts. I replaced that chip. Remember that this is the signal that was missing. And that goes down and enables this other counter, which you can see now is counting. And there is the vertical counts now, all the way down. And we do have vertical counts all the way down, and that's actually the terminal count on the last one. So, all right, but we still have no access to these. And what I'm doing right now is I'm just looping a random write at 4,000. So I'm trying to write into these RAM, just looping it. And right here is a signal called CPU write. And if I get on CPU write, you can see right there, CPU write. and it's not doing anything. You can see where that auto is flashing up here. That means it's not triggering at all. So there is no signal on this at all. It's just low all the time, which I'm going to have to pull out the old VFB schematic and let's find this CPU write. As I imagine that's supposed to do something when the CPU is trying to write, right? Here's V256. And there is V256, which is 60 hertz. You see where it says 60 hertz up there? So, yeah, that's looking good. So we're getting there. We're getting some signals. Here's RAM write enable, which isn't doing anything either. I don't know what's going on with this, but nothing's going on. Here's memory read. And no memory read, but that shouldn't be because we're trying to write, right? CPU write should be doing something, I would think, and it's not. So let's get the VFB schematic out and see what we can see. Okay, I have moved the fluke just to run on the board. So we should be trying, the system should be trying to access the RAM. It's trying to run. So I started with test point 6, which is, oh, it comes down, oops. Yeah, it's folded. It's folded up anyway, I think. Yeah. Test point 6 comes down here, and it's fed off of this 109 right here. It is the Q not. Pin 9 is test point 6, which is CPU write. So if we go to 3E, which is the 109, and 3 to the E, here's E, 1, 2, 3, right here. We have a pin 15 is a clear signal. So it's clearing, so that'll clear it low, that'll clear Q low. Here is our J, which is always low, and K, which is a toggled thing, and here's your clock, and a 1, and then Q is low all the time, and Q naught is high all the time. Now, the way a 109 works, don't just assume that this is stuck low and this is stuck high. This is a clear. Now if we look here, J is low all the time. That's weird to me because J is not tied low. J, pin 14, comes down and is input off of 5F. So before I assume, I'm going to assume this is a timing issue and that's not, Q and Q naught are not toggling because of timing, because J is always low. Because how that works is if you look at the data sheet here, I've got notes on the data sheet. This is how a JK flip-flop works. If both J and K are 0, then on the rising edge of the clock, Q goes low, Q naught goes high. That's what we're seeing right now is Q naught, or Q is low and Q naught is high all the time. Now, the only situations that we're going to have are right here because J is low all the time. So on the rising edge, in this scenario, you'll get a toggle situation, right? You know, Q and Q naught will just toggle, simply toggle. So what I'm thinking is that on the rising edge, it's probably during a clear or it's in this state on every clock. That's what I'm assuming. Before I go analyzing this, I'm just going to dig further back into the schematic. So I'm going to follow 14 down into this business. So 5F, I'll look at 5F, which is a 0, 2, 9 and 8 out to 10. 9 and 8 out to 10, which is this 02 right here, 9 and 8 out to 10. So here's 8, which is always high. Right there, that tells me that this output will never be high. It'll always be low, because in NOR gate you have to have lows to get a high. So you can jump right to the output and see the output is always low. This is the other input. But we have an always high, and that's what's going to, what is that going to? That's what's going to J, right? No. That's what's coming from 2E. If we look here at the schematic again, pin 8, which is always high, is coming from the 32 at 2E, the last gate, pin 13, 12 out to 11. So if we look at 2E, which is this guy, 2E right here, and we go, and this is an OR, and we have a funky looking signal right there. That don't look good. And we have a right there, but we're getting a high all the time because of this. This is the signal that's no good. That's reading as a high all the time. And that is pin 13 of that 32, which is coming from 3F, the LS10. And that's a not AND gate, 3F. And 3F is right here. It's this guy. And it's the 1 2 13 or 1 2 13 out to 12 gate. So a not AND, the way a not AND works is to get a low you have to have all ones. So we need to see some toggling or all ones to get a low. So that looks good. We've got ones in there. That looks good. And then there you go, there. Toggle. That looks good. We should have lows on here and we don't. That's the output. So that is the bad chip right there. So we're going to go ahead and stop and replace this guy, the 10. But before I do that, I think I'm just going to generally go around really quick and probe some signals and make sure, see if I can't catch anything else that is just obviously bad. Because I don't want to have to keep taking things apart, and if I can find multiple bad chips, that'd be great. This one's definitely no good, but I'm going to continue and just probe some of the more general, basic, easy stuff. So we'll see if I can find anything else right off the bat that's bad. Be right back. New LS10 in the board. So we're going to go ahead. I got the fluke hooked up. I'm just going to do a run and we'll count these flashes and see if it passes that test now. And whoop, 1, 2. There it goes. It actually did. Let's reset. 1, 2, 3. Here's the RAM test. 4. It passed the RAM test. 1, 2, 3. RAM test. Pass. And the 4th test, I think, is this board. So let's do some RAM shorts on this and see if this thing's actually... Hey, we're doing RAM checks now. Check that out. That's a pretty long test. I'll come back. Okay, and I am doing a test on the second RAM range. 6000 to 7 FFF. The first one came back okay. The 4000 to 5 FFF, that was fine. So it's looking like this thing had, well, it had all them bad fuzzy chips. It had all them bad RAM. We put in new sockets. These two chips were bad. Yeah. Cleaned it up nice. And our CPU is now talking successfully to all of this RAM. Should be any second. There we go. Good. CPU is successfully communicating with all of this stuff. So I think we're good on this board now. Unless there's another problem that shows up in gameplay with flaky graphics of some sort. But as far as booting and the CPU is concerned with the game booting, we're good. This is where the problem lies now. That fourth beep, I'm pretty sure, is this guy. And we can actually look that up because this thing has tests. It's the test after the RAM test. This is the one that we were stuck on. The third self-test. And then it flashes. The fourth flash means that this is good. And we've gotten past this. So the next one is, yes, the fourth flash tests the RAM circuit on the BSC 1000 color board. So basically it gives you stuff to check, which is kind of cool. But it could be anything on that board. We know the RAMs are good. Remember, I used the Inquisitor and tested the RAMs. So it's definitely this board. And that range for the color RAM is RAM short at 8000 to 87FF. And that's actually two sets of these. And you can see it's doing something. So it is actually doing something. But it fails. And this is always the same thing. It's a decoding issue. So, yeah. So we have an addressing error, and address multiplexers are right here. There's probably an issue with these, or something feeding into these, or controlling these, I should say. So we'll look through this and we'll figure it out. It could be it could be disguised as a data problem. It could be a data buffer. Who knows? And then it's kicking back a RAM addressing error. I've seen weird stuff like that happen. So in this next section, we'll go through this what is it? The BCS or BSC? It's the BSC 1000. We'll see you then.